In this lecture, we will discuss a new family of data models. If you have learned something about the recent very hot topic of deep learning, you might have already heard the model of neural networks. By deep learning, normally we mean that we use neural networks of very large number of layers. That is just a specific kind of construction of neural networks. So let us um, have a review of linear models, which we have discussed in details in the previous lectures, and that is the building block of neural networks. A linear model, core of a linear model is some value that is the weighted sum of all the observable attributes of data samples. And we will construct the quantity that is of interest, such as the class label in a classification problem, or the probability of a sample belongs to different categories in classification, multi-class classification problem, or the value that is to be predicted in regression problems. We construct the prediction target, use the weighted combination of the attributes, and that makes a linear model, or that is the idea, the core idea in a linear family model. And note that I have explicitly write out two equivalent representation of a linear model. In one, we adopt a special parameter that is a bias, a constant that we set as offset of each of the weighted combination. On the other hand, we will adopt a particular singular input attribute to be constant one. To be constant one, and adopt a special weight for this constant one attribute, which serves as the bias. So they are equivalent. We will use either form for the convenience in the discussion context. The linear model is connected closely to a neuron in a way that the first generation of linear model, which is the perceptron, what we have discussed previously, was actually inspired by the biological neurons. So as an information processing unit, it accepts some number of attributes, and it gives different weights to each individual attribute. And by collecting all the weighted contribution from the attributes with optionally a bias, then it will adapt some kind of processing which is nonlinear map from this weighted sum value to the output. For example, we can adopt a sample judgment to see whether the weighted sum is greater than or less than 0, and correspondingly output a -1 or a +1. Or otherwise, we can adopt some nonlinear functions, which I will discuss this function later. This makes a basic building block of, this is a basic linear model, and it's also a basic building block of neural networks. To extend such a building block into neural networks, let us discuss a few different ways in which we can extend the block. Actually, there are multiple aspects where such computation, such a processing unit could be extended. I label them as A, B, and C. This is a rough categorization. This is not technical taxonomy, but I just want to give some intuitive understanding about those extensions. We can do something more in the stage of mapping. We can do something about how to collect the weighted contribution from the attributes, and we can also do some clever things in the attributes themselves. So let's start from the most obvious techniques. After collecting the weighted contribution, we need to adopt some nonlinear transformation to get the final output of a neuron. Why there must be some nonlinear transform? For this question, we will discuss a bit later, and you will consider that by yourself in a quiz question. Well, what is important here is the mapping from the input, that is the weighted sum and the weighted contribution from the attributes, and the output, that is the final output of this neuron, this unit, this block, must be nonlinear. It cannot be a straight line, but any shape other than a straight line will do. Some very often adopted function is this kind of a sigmoid function. Sigmoid function is a name that reflects intuitively the shape of the function. It maps all the values, all possible values of the input sum, which is actually all the real values, in the range from 0 to 1, which can be useful in classification scenarios, binary classification scenarios in particular, because then the weighted sum can be treated as some kind of plausibility measure. You need only let the model to output such a plausibility measure, and the nonlinear transformation is responsible to convert whatever kind of value between the range of 0 and 1, which can be interpreted as the confidence that the model thinks this sample belongs to the positive class. And correspondingly, if you take 1 minus this value, that would be corresponding to the negative class. But this need not to be the only solution if you are considering classification problems in using such a block. For example, the perceptron strategy is another method which directly map all values that is less than 0 into -1, and all values that's greater or equal to 0 into +1. This is another nonlinear transformation. It is a step function. You take a step at a particular value, and this is very often used in the final output of the classification network, and this can be used in other scenarios, which we'll encounter very soon. On the other hand, as we have discussed, as long as the shape is not a straight line, you can use this to build complexity in the computation procedure. Then how about let us to do something that is as close as to straight line, but which makes things simple enough, but it's not straight line. So we can make this, well, you can bend it or turned or broken line where you have a special point at which the direction onto which the line extend changes. In this way, in this particular example, you output a constant value 0 when the activation, the pre-activation value, that's weighted sum is less than 0, and we output y equals x when the x, well, in this case, the weighted sum is greater than 0. This is actually what is very widely used in modern neural networks, because this kind of shape keeps complexity of the network and keeps computation as simple as possible. There are other ways to extend the network. For example, in the original construction, the sum unit here collect weighted summation of all contributes and give this to a nonlinear transformation and give this to the nonlinear transformation. It will output the final value that's produced by a neuron. From now on, let us call that neuron because we will use this as the building block of neural networks. So for this basic neuron, we can adopt other ways to let the input information pass to the output. So we keep the original structure the same in this part, but instead of using the output of the nonlinear transformation as the final output of this neuron, we can also let the input information directly contribute to the product of this neuron by adding the output of the nonlinear transformation and the original input attributes, and let the sum to be the final output of the neuron. Of course, I will say here, but you will realize the limitation later when we have established how a neural network, the complete model of neural network. Here we implicitly introduce a constraint that in this way, one stage of the computation in the neural network, which we often call a layer, which makes multiple units of neuron units, the number of the output must equal to the number of inputs, and that is to say, for how many attributes as the input of this stage of computation, in the same stage, we must employ the same number of basic neurons so that the output has a very exactly same format as the input, and then they can be element wisely added together to generate the final output of this layer. The advantage of this construction is it makes the computation simpler. Although it may look like the structure is more complex, but it adds information freeway on which the information in the input variable can pass to the output of the network quickly, and therefore, when it comes to the training of the network, it will be more efficient to calculate how to adjust model parameters for early computational stages. And thirdly, in this part, we can extend a linear model at the input attributes. This construction is a core idea of neural networks. We have already encountered similar ideas. If you recall what we have discussed In the extended linear models, the lecture we discuss linear model 2. In that lecture, we consider two aspects. One, feature extension. Instead of using the raw observation from the data, we can construct different features from the data and use the features to construct linear models. And we have discussed that linear models has two kinds of linearities. One is with respect to the input features. So the output of the model is linear with respect to, or not the output of the model, the core value, that is the sum of the weighted, the weighted sum. This value is linear with respect to the attribute, and it's also with respect to the weights. And the linearity with respect to the weights is the namesake for linear models. That is why linear models are called linear. While on the other hand, we can freely adopt transformations in the input attribute so that the model construction is more conductive, is more effective to solve the prediction tasks at our hands. And the second part of linear model 2 as a review is that we have introduced the support vector machines. And lastly, we have established that by adopting the kernel trick, we can combine these two kinds of extension together so that the support vector machine is actually work on a very high dimensional transformed feature space. And that space could be of infinitely dimensional, if you recall that. And in the following discussion, we will consider an alternative way of extend those attributes. Instead of manually design feature transformation or to adopt kernel tricks to seek for automatic transformation into a lot of features, possibly infinite many features, we adopt a recursive design of the extension. So how about instead of designing this G1 and G2 to generate this X1 and X2 manually, we adopt another two neurons of the exactly, or maybe not exactly, but of a very similar structure as a neuron, and use the output of this primary layer of neurons as the input of the secondary layer neuron. And this idea of recursive construction gives us the model of neural networks. In the next video, we will consider the specific computation of neural networks and the efficient representation of the computation.